So I will give a presentation mostly focused on what I did during my PhD thesis. But if we have some time at the end, maybe I can say a few words about the project I'm currently working on. Of course, I prefer my presentations to be interactive. So if one of you has any very important question, feel free to interrupt me and ask me your question. And also, sorry for the coughing. I've been sick for 1 month, so hopefully it should be okay. So my presentation is entitled Graph Neural Networks for Power Systems. So between 2018 and 2022, I was a PhD student at RTE Research and Development and Université Paris-Saclay. So my work was mostly focused on trying to develop graph neural networks that would be suited for power systems application. And that's basically what I will present today. But you should also know that right now I'm working as a postdoctoral researcher at Institut Montefiore, so Université Liège, and also at RTE, Research and Development, where I'm trying to apply what I've done during my PhD thesis to a concrete problem, which is the problem of managing voltages in the transmission grid. And the goal is really to develop a prototype in the short-term future. Okay, so let's begin. So my PhD thesis is called Deep Statistical Solvers and Power Systems Application. Maybe Antoine, can you tell me a bit what is the general background of the people around here? Are they more familiar with power systems or with deep learning, or both?
I would say the general background is OR, but okay. So and with an interest in power system, but that does not mean that some people do not have a strong background in either deep learning or power system.
Okay, so then that's perfect. So first of all, I will give some background and some how can I say it? Give some motivations for why we are trying to use deep learning and apply it to power systems. So at RTE, which is the French transmission system operator, there are some people that we call dispatchers, and that monitor and control transmission grids in real time. So those are people that are constantly monitoring a big screen, just like the one you can see here. Okay, and they have to make sure that there is no overflow or that there is no event that can endanger the power grid. Otherwise, there can be a blackout, which will be extremely bad. So in order to make sure that all this system runs properly, they have to run a lot of security analysis to check for every possible contingency, check that the system can withstand it, and they have to anticipate the near future. So they have to run these security analysis for for instance, the next 24 hours. They have to make sure that everything will be okay. Okay, and in order to in order to solve to run those security analysis, the most common computation that you have to make is solving the AC power flow problem, okay, where as input you have some production and consumption, which are defined at nodes of your grid, okay, and you also have some line characteristics, which are the resistance, reactance, which are also linked to the length of the transmission lines, etc., which are physical coefficients that are defined at every edge. Okay, and then they use a Newton-Raphson method, okay, which works very fine, and that gives them the voltages at every node, okay, and also the power flows through every line. And they have to make sure that the flows remain below a certain threshold and that the voltages remain in an acceptable range, etc., etc. Okay, great. The thing is that power systems are facing an increasing uncertainty and complexity, as you may all know, mostly because of intermittent renewables. Also in Europe, because of new market mechanisms that push energy producers to change their plans on a very short notice, on a very short schedule, and also because of new electricity uses. So what was a reasonable way of managing the grid in the past will not be necessarily a good way of managing the grid. So that's why we want to make sure that the system will remain in an acceptable state using probabilistic approaches such as Monte Carlo methods. But the thing is that Newton-Raphson is currently too slow to perform an in-depth statistical analysis of all the possible futures using Monte Carlo analysis. And we may want to replace the Newton-Raphson method with something faster that could, for instance, come from the artificial intelligence domain. Okay, so why artificial intelligence then? So AI, and more specifically deep learning, has achieved tremendous successes in various domains. So computer vision, natural language processing, and also games. And I'm pretty sure you all know about ChatGPT, which is something really incredible. And the common pattern here is really that deep learning is very good at solving complex problems, which require a very high level of abstraction with regards to the data that you are considering. So, which is something that we want to exploit also for our power systems applications. Okay. So now, let's say we want to replace the Newton-Raphson. Okay, so we want to basically find a mapping between some production and consumption and some line characteristics and some voltages and power flows that are defined at every node and every line of a power grid. Okay, so we will want to use machine learning and more specifically deep learning, but still I will give a very brief introduction to machine learning for those of you that may not be familiar with these concepts. So let's say that you have a bunch of data points, okay? So you have here the x-axis and here the y-axis, and you have all those data points, okay, which you collected from measurements, for instance, okay? And you want to be able to predict what will be the next, what will be the value of y, knowing the value of x. So let's say that you have now a new data point here, let's say, a new value of x, you want to be able to infer what will be the value of y. And that's why you will learn an approximation f theta that learns a mapping between x and y. And having learned this function f theta, you will be able to infer the value of y. Okay. And the process of learning is really the minimization of the error, meaning minimizing the distance between the prediction of your function, okay, and the actual value that you have collected using measurements by modifying the parameter theta. Okay, so really the process of learning is trying to minimize the error over a certain train set. Okay. Just to check. Okay. So here, for instance, the most basic approach for us, if we want to replace the Newton-Raphson, would be to feed some power grids, which are sampled from a certain probability distribution. So here, the P denotes the empirical distribution, meaning all the big databases we have at RTE with all the possible states that have occurred in the past. Okay, and you select you randomly select a power grid, you feed it to your regressor, to your parameterized function, and you also feed it to your Newton-Raphson method, okay? So now you have two predictions, okay? And you will measure the distance between those two predictions. Okay, and you will try to minimize the distance between those two by modifying the parameter of your parameterized function. Okay, and this is what we call in my PhD thesis the proxy approach, where we simply try to imitate, we try to learn an approximation of the Newton-Raphson method. Okay, and here for f theta, we actually want to use deep learning. Not only because it's a buzzword, but also because it's very efficient at learning complex nonlinear relationships between variables. So once again, I'm going to give a very brief overview of what deep learning is. If something is not clear, feel free to interrupt me, and I can hopefully answer your questions. So basically, deep learning and deep neural networks is really just a subdomain of machine learning, which is concerned with a certain type of parameterized function. Okay, so here I have denoted it as f theta. Okay, and in these deep neural networks, you basically process your input data through several layers. So here you have your data. Let's consider that it's in 3 dimensions. Here I have tried to encode the values of the scalars using color. So let's say that black is for -1 and white is for +1, or the opposite, whatever you like. So here in the inputs, you will basically multiply all those values with your weights that are stored in your neural network, okay? And it will produce a hidden layer. So here it's in 4 dimensions, okay? And then you will once again multiply all those values with a list of coefficients, okay? You obtain now something that is in 3 dimensions, and then you do the same thing again with some other coefficients, okay? And now you have your output. And basically the process of learning your deep neural network is really the process of learning how strongly connected each neuron should be, okay? And you will learn that by minimizing the error between the output of your neural network and the actual ground truth that you want to imitate by modifying the different weights of your neural network. And this is performed by using the backpropagation algorithm, which I will not explain right here. Okay. The thing is that standard neural networks are only well suited for vector data. I mean, if you take a look at this picture, and if you try to feed your deep neural network with an input data that will be slightly larger with one additional component here, you will see that your deep neural network will not know what to do with this additional value. And exactly the same, if you forget to provide one component to your neural network, the neural network will not be able to process your data. So there is this very profound and very important assumption that your input data should be always of the same size, and also the same is true for the output. It should always be of the same size. The thing is that power grids are graphs and have a varying size and structure. So here I have represented what power grids actually are. So here you have one big power grid with some features that are defined at nodes and some features that are defined at edges. And among those features, we can split them between the input features and the output features. So here for our AC power flow problem, the input feature will be, you probably guessed it already, will be the injections at every node and the physical coefficients of every transmission lines for every edge. And the outputs will be the power flows and the voltage magnitude and phase angle. Okay. And we basically want to learn mapping between those features and those features. Okay. Okay, so the target optimization problem is the following. So as input, we have production, consumption, line characteristics, and as output, we have voltage and power flows at every node and every line. Okay. And basically what the Newton-Raphson does is that it tries to minimize the violation of physical laws. It tries to find the outputs that will respect Kirchhoff's laws, okay, which can be rephrased as an optimization program, which is right here. So we want to find the y star of x that minimizes the violation of physical laws. So here L is really a small function that quantifies the violation of physical laws. Okay, and the holy grail is really to find a mapping f theta, okay, that will provide for every possible power grid, that will provide the state y, that will minimize the violation of physical laws. And we want to do that not only for one power grid, but for a whole distribution of power grids. So that's why we are considering here the expectation over x, where x is sampled from a certain distribution P. Okay, and in this distribution, of course, you can have varying feature values, but you can have also varying topology. So you can see that here you have a power grid with only 2 nodes, and here you have 4 nodes. Okay, and we are not actually only doing that just for the sake of it, just because we think it's beautiful or interesting. It's also because in the data we have at RT, from one snapshot to the other, you do not have the same amount of nodes, and you do not have the same amount of yeah, mostly nodes. The reason why is that at RT, and I know it's something that is not done a lot in other countries, but at least in France, that's a thing that people really like to do, that they can split nodes. So that the principle is quite easy to understand. So you have several lines that are connected together at a certain substation, okay? And the dispatchers can rearrange the interconnection pattern so that, I don't know, those lines will be connected together, but the other lines will be disconnected from the other. So now, instead of having one big node, you have 2 separate nodes. And this happens a lot. This happens daily, hourly even. So that's why we need to take the varying topology into account also in our problem. Okay. So we basically want a neural network that can minimize the violation of physical laws, and that can do that for a whole distribution of power grids where you can have varying topology. Okay. So first of all, before diving into the topological aspects of it, I want to emphasize the fact that we know what the Newton-Raphson is actually trying to do. We know that the Newton-Raphson is actually trying to minimize the violation of physical laws. So why not take advantage of it and try to directly learn our deep neural network, f theta, by minimizing the violation of physical laws. So that's what we call the statistical solver approach, which is highly related to physics-informed neural network, for those of you that know about it. And the idea is really to, oh, sorry. Connexion perdue. Okay. Should work again. So we feed a neural network to our, a power grid to our neural network. And then based on the prediction, we can compute the violation of physical laws. And we simply have to try to minimize it using backpropagation, okay, and using a stochastic gradient descent to train our neural network. So by doing so, we are completely getting rid of the Newton-Raphson method, which can sometimes be slow, and that also can have some convergence issues in some cases. Okay, so now that things are a bit more clear, so we want basically f theta that will be probably a neural network, and that can minimize the violation of physical laws for a whole distribution of power grids. But what kind of function should we use for f theta? So you probably remember from what I said earlier that using a standard neural network, so multi-layer perceptron, which are also called fully connected neural networks, is not a good idea. Mostly because you always have to provide it with a constant size vector. Okay, so let's consider the case of using a standard neural network, because we want to be sure that it's not that good of an idea. But let's consider the case where we have standard neural networks. Okay. And first of all, let's consider what's a key property of the Newton-Raphson algorithm. So let's consider here a very simple power grid, okay, that looks like that with only 4 nodes and 4 transmission lines, okay. So we apply the Newton-Raphson method to solve the AC power flow problem. And we obtain some values for the voltages and also for the power flows. And these values minimize the violation of physical laws with regards to these inputs. So we obtain a violation of physical laws that is almost 0 to a certain precision error. Now let us apply a permutation over our input data. So a permutation is simply a node reordering. So 1 becomes 2, 3 becomes 4, 2 becomes 3, and 4 becomes 1. So here, it may seem a bit strange to do that, because as you can see, it doesn't change the graph at all. But the thing is that for your computer, it changes your data a lot. Applying a permutation to this input data from a computational point of view will produce something that is very different from the input. So basically what I'm trying to say is that your computer will not see that this and this are exactly the same. It won't be able to detect it directly. And now if we apply the Newton-Raphson method over this permuted data, we obtain basically exactly the same output as before, but now there is a permutation over the nodes. So 1 has become 2, etc., etc. Basically, when we have applied a permutation over the inputs, it has also resulted in a permutation over the outputs. And we obtain something with a violation of physical laws that is extremely low. Okay, which is great, because physical laws are not affected by a simple permutation. Okay, so now let us consider the case where we train a standard neural network, so a multi-layer perceptron, over a data set that would be made mostly of power grids that look like that. Okay, with this specific topology. At some point, your neural network will become, will become extremely good at predicting the actual value, and you will obtain a violation of physical laws that will also be very low. So, and you will be actually quite happy about your standard neural network, it will be a very nice proxy of your Newton-Raphson. But now, if you apply a very simple permutation over your input data, so the exact same permutation I just applied a few minutes ago, and you try to predict the Y using the standard neural network that you have trained before, you will obtain something that is completely messy, that has no meaning, and something that actually returns a very large variation of physical laws. Because your standard neural network will not be able to understand that you have applied a permutation over your inputs. The thing is that standard neural networks are not permutation equivalent, which is very problematic for us. Because we know that the Newton-Raphson is itself a permutation equivalent operation, and we are trying to approximate it with something that is not permutation equivalent at all, which is kind of a problem for us. Maybe I just want to emphasize here that it is a problem for us at RTE, mostly because there is some variability in terms of topology in the datasets we have. If you were to consider a dataset where all the power grids have exactly the same topology, and you are 100% sure about it, then of course your standard neural network will be more than enough. It's just that for us, for the specific case of where you have varying topologies, you have to put a bit more effort in it. So that's why we want to use graph neural networks. So there are many ways of doing graph neural networks, and I would argue that there are as many different graph neural networks as there are researchers working on it. So I will give you my version of it, but of course that's probably not the one you will find in the literature. And also there are many different subdomains in graph neural networks. So here I will show you a message passing graph neural network, which is basically an iterative process that propagates information locally. Okay. It is mostly composed of 3 different steps. So you have at first the encoding step, where you apply a neural network, very simple neural network at every node and at every edge, so that you can encode the input values in a latent space. Then you have some message passing, where you propagate information locally from neighbor to neighbor, basically. So the operations remain extremely local because you only take a look at your direct neighborhood, but still there is some information propagation. And then there is the decoding step, where you convert the latent representation of every node and every edge, and you convert that into something that has a physical meaning, that has some physical units that you can inject in your program. Okay, so I want to give here an example of what a graph neural network does, because I think it's always better to have a nice thematic to really understand what's going on. So let us consider here this very simple power grid. Okay, so here we have 3 nodes. Okay, and we have 2 transmission lines. Okay, so the input data for nodes are in 2 dimensions. Okay, and the input data for edges are in 1 dimension. So that's our input. And now we apply the encoding. And what the encoding does is that for every node, so for every vertex, it will apply the same neural network. Okay, and it will convert the input into a latent representation. So here it's in 3 dimension, but whatever you like. So okay, and you will apply the exact same neural network here, here, and here. So there is some form of weight sharing across the grid. Okay. And also you will apply a different neural network that will be specific to edges at every edge. So here you apply your encoder here and here. Okay, so now you have a latent representation of your graph. You can see that it is still a graph. It still has 3 nodes and 2 edges. And you can see that at this point, there was no propagation of information. There was no sharing of information between neighbors. What we did here is extremely local. Okay, so now we apply the first message passing operation. Okay, let's focus first maybe on the top part of the plot. So we basically use a neural network here that is specific to vertices and that will update the state of this node. Okay, and to update the state, so it takes as input, of course, the previous state of the node, but also it also takes as input the latent representation of the edge it is connected to, and also of its direct neighbor. So it takes this as input. Okay, so here there is already some propagation of information, but it's always, you know, a one-step propagation. I mean, we are only looking at direct neighbors. Okay. We use exactly the same neural network here for this node to update the latent state, but now so we take as input the previous state of the node, but we also take as input the information about the direct neighbors. Okay. And here for this one, we do exactly the same. So we have a one-step, a simple one-step message passing operation where we take as input the information from the direct neighbors. Okay. And it produces a new state for every vertex. And we can do the same also for edges. So now to update the state of every edge, we take the previous state, but we also take as input the states of the nodes it is connected to. Okay, and now we produce a new latent representation of the edge. Okay, and we do the same here. So those 2 neural networks are exactly the same, and then those 3 neural networks are exactly the same. So once again, there is this idea of weight sharing. Okay, and now we can do another message passing operation. Okay, and then another. Okay, and once we consider that we have propagated the information enough times, we can stop and decode. I just want to emphasize that at this point, there can be no influence from this node to this one, because as you can see, there is no direct path between here and here. We can go as far as there, but not here. So we need to have enough propagations so that the information of every node can reach every other node. Okay, and once we consider that we have propagated information enough times, we can simply decode it. So really the idea of decoding is really to embed your latent representation into a space that has a physical meaning, that has physical units. Okay, so now we take the latent representation of every node, and we apply the exact same neural network here to produce here, in this case, a one-dimensional output. And we do the same also for edges. So we use exactly the same neural network here and here, and we produce a prediction for edges. As you probably guessed it, it only relies on local operations. All the neural networks that I used here, which are very simple multi-layer perceptron, are trained jointly using backpropagation. So yeah, and also it's a mapping that is permutation equivalent. So if I change the ordering of the nodes, it will also result in a reordering of the output. You see, And what's even more interesting for us is that if we were to add some nodes to our graph, so let's consider, for instance, that we have one additional line and one additional node, okay, then we would simply do exactly the same. So we will use the same neural network here, and then we will have a small propagation step here. So we would have something like that. So yeah, basically, sorry, I cannot really add it on the fly, but the idea is that whenever you add some nodes or some edges, your neural network will still be compatible. I'm not saying that it will output the perfect result, but at least from a mathematical point of view, it will still be compatible and still be able to produce a prediction. So that means that using this kind of graph neural network architecture, you can work on data that has varying topology, which is something that is not possible using multi-layer perceptron. Okay, so we decided to call a graph neural network that is trained so as to minimize the violation of physical laws, a deep statistical solver. So why deep? Because we use deep learning, and statistical solver because we are really trying to train a heuristics that solves the AC power flow in our case, but that consider a statistical problem. I mean, we are trying to minimize the violation of physical laws for distribution of problems and not for a specific power grid. We also have, so yeah, I have something like 4 minutes left, so I will be short. So we have also developed a universal approximation theorem during my PhD thesis, just to be sure that what we are doing here is well grounded in a theoretical point of view. And what we found is basically that graph neural networks can approximate an actual Newton-Raphson solver to an arbitrary precision, which is great. So once again, it's a universal approximation theorem. So we are not saying that it will necessarily converge towards the exact solution, but we are saying that we are considering a space of approximator that is dense in the space of functions that we are trying to imitate. So what we found also that is very interesting and also quite easy to understand is that you need more propagation steps than the largest graph diameter that is in your distribution. So you can see it as the following. If you want information to propagate from any node to every other node, you need to have at least you need to have an amount of propagations that is larger than the largest diameter. So the diameter of a graph being the largest smaller distance between any two pair of nodes. So if you're applying less propagations than the graph diameter, then you know the impact of every node will remain too local to have an impact over the whole graph. And we have some theoretical proof for that, which is great. So we also conducted some experiments. So I will be very short on that. And there are actually much more experiments, many more experiments in my manuscript. So if you're interested, you should take a look at it. And here I will give maybe the most basic ones. So we consider two distinct data sets, one that is based on the IEEE case 14 power grid, which is a power grid that looks like that, with 14 nodes, and another data set that is based on the IEEE case 118 with 118 nodes, looks like that, okay? So we have some random injections, and we also have some random line disconnections, also to have some topology variability. Okay, so here you can find the two different data sets. Okay, here in this column, and in this one, you have the results of the deep statistical solver, which is the process of learning a graph neural network in an unsupervised fashion by directly minimizing the violation of physical laws. Here you have the results of the proxy, where you use a graph neural network, but by directly imitating the output of the Newton-Raphson. So it requires to call the Newton-Raphson to have the ground truth. And here you also have the output of the Newton-Raphson. So here, in this one and in this one, we computed the correlation with the Newton-Raphson. So that's why this column is empty. And here we computed the normalized root mean squared error with the Newton-Raphson. Okay. And what we observed is that in terms of power flows, we obtained very good correlation for both the deep statistical solver and for the proxy. So our deep statistical solver is very good at predicting power flows, so in active and reactive. Okay, so here and here, and also here. What we also observed is that the proxy approach is very good at also predicting the voltage, phase angle, and magnitude. So here. But the deep statistical solver is slightly worse. Yeah, even a lot worse than the proxy approach in predicting the voltage, phase angle, and magnitude. Okay. The reason why is that in the deep statistical solver, the loss function that we are trying to minimize is expressed in terms of power. So it is actually expressed using these quantities. So that's why the correlation is so good here. While in the proxy approach, we try to imitate the output of the Newton-Raphson in terms of voltage, phase angle, and magnitude. So here, the loss function of the proxy approach is expressed in terms of voltages. So that's why the proxy has a much better correlation for the voltage, phase angle, and magnitude. But never mind, it really depends on the application that you consider. If you are mostly focused on power flows, then the deep statistical solver is more than enough. Okay. Okay, so as a summary, we have designed a full-fledged optimization method that is trained by direct minimization of physical laws, that aims at solving a distribution of problem instances, that respects the permutation invariance of the problem, that relies on the training of a graph neural network heuristics, and that is theoretically grounded by a universal approximation theorem. Okay,